your raw data. Then you stick that into your algorithm. You probably want to do something called cross-validation that Adrian will talk about later, which will tell you how good your model is. And then you do your model evaluation and you try to figure out, you do your actual predictions. That is sort of like the high-level view of how machine learning works. There's hundreds of algorithms. Here's like, we're going to later talk about more about scikit-learn, which is one of the major packages. And depending on what kind of problem you have, you can like try to make your way through that. I always end up here, like always, and then it just says tough luck, and then I like go back to my Bayesian statistics. It's like, okay, fair enough. Yeah, so there's like lots and lots of algorithms. There's lots of good resources out there to just learn the maths of it, so we're not actually going to tell you much about the maths. Some terminology. What comes up a lot, and what will come up several times here, is the term linear model. And that's just a model that's linear in the parameters. The stuff that you can put in there can still be nonlinear. Like one feature could be your data squared. That could be a feature, but it's always linear in the parameters. As opposed to a non-linear model, there's a lot of models that are linear, like logistic regression and support vector machines. There's a lot of nonlinear models out there, and among them are decision trees, random forests, and neural networks. So all the cool things are nonlinear, which is a problem. Nonlinear models have the advantage that they are far more flexible, but as I'm going to tell you later, is they are much harder to interpret. I'm also going to probably mention several times the term generative model, and that's just like a model that can generate the data you're trying to look at. So for example, if you have an X-ray spectrum and you fit a power law to it, that power law is a generative model for the spectrum that you've actually seen. So when is machine learning useful? Let's first talk about humans. So Galaxy Zoo is a project that classified around 9,000 galaxies by having people look at them and click through some questions. And that found a few things. Humans are excellent at pattern recognition. I probably don't need to tell you that. Humans are also able to find the unexpected, which is really important. Like this thing, which is a big nebula that was just found by a school teacher by chance. And that then results in several publications. But the problem is that humans don't really scale. And for example, LSST will detect 10 million transients per night. That's a lot of PhD students you need to like pay and keep awake during the night, and that's probably not going to work. Humans are unfortunately also biased classifiers, and that's always something you have to take into account when you do machine learning that takes in that uses classifications made by humans. For example, in Galaxy Zoo, people classify more galaxies as rotating anti-clockwise than clockwise. And so the question was, are humans biased classifiers, or is there a preferred rotation in the universe? And having a preferred rotation in the universe would have been really weird. So they were quite glad that they'd figured out it's just humans. But essentially, like a lot of future instruments produce data that's too big to be analyzed by hand, which is where machine learning comes in. Machine learning has the advantage that it scales to large data sets because computers are easier to scale than humans. You have fewer human biases. I can't say no, because especially if you have biased training data sets, you will always get biased results. You can only ever find what's been seen before, especially in supervised learning, where you basically put in some training examples and you try to reproduce those in a larger data set. Here's an example that Adrian gave me. This is the HR diagram as seen by Gaia. Does anyone notice something on that HR diagram?
There are error bars.
Pardon?
There are error bars.
Ignore that. Like, does that look like a typical HR diagram to you? Why not?
Aha.
It seems y is bigger, its spread is bigger, b minus b.
So the main thing it's missing is the white dwarfs.
Oh.
There's like basically no white dwarfs in Gaia. If you use that to do classification, you will never find any white dwarfs in the universe because they're not in your training data set. And that's, a problem. So be really careful with that.
Wouldn't an algorithm tell you I have no idea what I think is? Or would try
But the
anyway
thing is,
to classify?
no, if you have a supervised classification and you don't have any white dwarfs.
Yes,
there are no white dwarfs.
Yeah, I understand that. The thing is, then you give another data set, and then
Right.
you return you this star is this or that.
Yes.
Right? If you don't have white dwarfs in your
Yeah.
training set,
Yeah.
but you give a white dwarf, what is the algorithm going to tell you?
It's going to probably classify it as that,
Okay.
depending on if you
So-
don't, because you don't have any options. It doesn't know what. It can only classify what it's seen before, and if it hasn't seen white dwarfs before, it will only classify it as something else.
But there aren't options to, like,
Yeah,
some
there
algorithm
are.
where it says that, like, no idea.
So what you can do is you can run this and try to use. So one good use of machine learning is to run machine learning on the stuff that you know.
Mhm.
And then look at the things that, for example, have a low probability in all classes, where the
Okay.
classifier says all options are bad, but I picked the best one of the bad ones.
Mhm.
And then you can look at those outliers. That's, for example, a good use
Okay.
of machine learning. But if you just like use a classifier, the classifier will only like tell you a bunch of.
Okay.
Machine learning models can be hard to interpret, and that's actually what I want to spend another few minutes on, because interpretability is really important to us as scientists. So what do I actually mean? Basically, I sit in a lot of machine learning talks in science, and I look like that. Not literally like that, but I'm like, you've done a machine learning model, but like, how does that connect to the physics we want to learn? How do you do that? And so here's an example I got from a book, I think, or a paper, or actually just the Astronomy website. And so basically this is a bunch of stars, and what your classifier did here is put a line through it and says everything on this side of the line is a variable star, everything on this side of the line is not a variable star, or possibly the other way around. Adrian can correct me. And then, sure. But the question is, are these all variable stars? What happens if you, for example, want to do population inference? What if you want to know, something about your population of stars? What happens to these black points up here? Are you missing parts of your population? And so that's a big problem, and that's where we get into the two main goals that you might have with anything that you do with data. And your two main goals are really inference and prediction. And so inference basically means you want to learn something about the system you're studying, the data, the system you're studying by looking at data, whereas prediction just means you want to be able to predict new data points. And so broadly speaking, inference is really the field of statistics, and prediction is really the field of machine learning. And so basically, so inference is just the conclusion reached on the basis of evidence and reasoning. And so, for example, why do stars have different colors from galaxies, or a different spectrum from galaxies? That's an inference question. Prediction just basically means if I have some like data points X and Y, what outcome will I predict for a new data point? That's a basic prediction question. It's like, in this image, is there a cat or a dog? And you don't really care about why the model said this is a cat or a dog. And that's a problem for machine learning because for us, because our scientific goal is almost always to uncover a causal relationship, whereas the machine learning goal is almost always to minimize prediction error. So what that means is the machine learning goal just tries to make sure you can classify as many things as possible correctly, but that doesn't always mean that it allows you to uncover a causal relationship. And in fact, it can mean that you actually run into trouble with trying to uncover a causal relationship. And your causal relationship that you do uncover can be really biased because there are biases that you haven't taken into account properly. So, repeat after in identifying weaknesses in the training data set.